All right, so we're going to take a look at circles in the coordinate plane. But first, we are going to review segment relationships inside of a circle. And we have our handy dandy formulas here. We'll remember that the chord product theorem will say that AH times HL will be equal to YH is equal to H or times HS. It's all written right here. So we're going to take a look at that for these first two problems. All right. So for question 1, we have two chords that meet, obviously, inside of the circle at point X. So we know that D times 6, or 6D, has to be equal to 6 times 12. Well, 6 times 12, I can make this a different color so it's easier to see. Sorry, I should have done that earlier. And a little bit smaller. There we go. Okay, there we go. Well, 6 times D is just 6D, and that has to be equal to 72. Well, now we'll divide both sides by 6. When I divide both sides by 6, I get D is equal to 12. So we know that this segment here is 12, which would make ZV 20. And obviously WY is 18. All right, so now we have this plate that's been broken. And we know that this chord is bisecting this chord, so this is 3.5, this is 3.5. Okay, great. Which means to find the missing part of the plate, I'll draw that. It's a very oblong plate. So we find this missing part of the diameter right here. So we will have 3.5 times 3.5, which has to equal 2 times, well, I don't know. So that's what we're trying to figure out. So 3.5 times 3.5, well, geez, a calculator would be super helpful right now, huh? Oh, I can get one. So looking for tools, math tools, pull up the calculator. All right. So we have 3.5 times 3.5. So we know that this product is 12.25. So now we'll divide it by 2. So we know that this segment here is 6 then 1/8, because 0.125 is 1/8, which means the diameter of the plate is going to be 8, because 6 plus 2 is 8, and 1/8 inch. All right. For problem 3, we're going to be looking at the secant product theorem. And the secant product theorem says that the entire distance of the secant times the part of the secant that is on the exterior of the circle is going to be equal to the product of the entire distance of the other secant times the part of the secant that is on the exterior of the circle. So we can safely say that we have QP, well, QP is 3 plus 5, 3 plus 5 is 8, times the exterior part, 3. And that has to equal, well, this entire distance from Q to R is 2 plus this X, right? Okay, so we're going to multiply the exterior part, 2, times X plus 2, because that's the distance of the entire segment. All right, so that means we have, check this out. Yeah, look at that. So then multiply 8 times 3, get 24. So now we'll divide both sides by 2, which will leave us with 12 times is equal to x plus 2. Subtract both sides by 2, and x is equal to 10. For our last problem, we have the, sorry, I'm going to yawn. We have the secant tangent theorem. The secant tangent theorem is very similar to the secant theorem, except we only have exterior parts of this tangent line. So we'll be multiplying the entire distance of the secant, in this case 16, times the portion of the secant that is on the exterior of the circle, 4. And then we are going to set that equal to the tangent squared, because the tangent only has one distance. So in this problem, we will end up with 16 times 4 is equal to x squared. Well, 16 times 4 is 64. The square root of 64 is 8. So the value of this piece right here is 8. So that's a quick little review of what we've been learning in the last couple of days. So now let's take a look at circles in the coordinate plane. So we have a theorem, an algorithm really, that tells us how to find the equation of a circle. And the equation of a circle is going to be written in the form x minus h in parentheses squared plus y minus k in parentheses squared, and that is equal to the radius squared. And we know that the center of the circle is going to be at point h comma k. So let's put this into use. So right here we have a circle, and we have the center and we have the radius. Well, that makes it pretty easy to fill this in. So we know that we'll have the quantity x, and we have the minus, right? So x minus 2, and that has to be squared. And we're going to add that to y. Again, we have the minus 2, and that will also be squared. And that has to equal the radius squared, and the radius is 4. 4 squared is 16. And so we have the equation of the circle for this radius, or that meets this specifications. And you don't have to take my word for it. We can prove it to you. Oh, it's draft day tomorrow. And so here we go. We have x minus 2 squared times y minus 2 squared is equal to 16, and there we go. We have a circle, which is showing the locus of all the points that are exactly 4 units away from 2, 2. All right, well, let's put what we've learned into practice for this one. Now we have the center of 1, -8, and we have a point on the circle, but that's it. We need to find the radius. So, oh geez, what am I going to do with this? It's a little different, huh? Well, I can safely write, oh, well, that goes over here. Okay. So I can safely write that we have an x value minus 1, because I have the center point, 1, -8. And so we have x minus 1 squared plus y plus 8 squared, because when you're subtracting a negative, it's the same as adding a positive, so that's the plus. And we have the radius squared. Wouldn't it be nice? Wouldn't it be nice if we had a point that we could plug in for x, y? Oh, we do. We have point j. So we can plug in 6 for x and 4 for y. So we can plug that in. 6 minus 1 is 5. 4 plus 8 is 12. So we get 5 squared plus 12 squared is equal to r. That's like a Pythagorean triple, isn't it? It looks a lot like the Pythagorean theorem. All right, so then 25 plus 144 is equal to r squared. 25 plus 144 is 169. And the square root of 169 is 13. So you'll notice that these circle equations are going to end up looking a lot like Pythagorean theorem problems once we start solving them. Well, how do we graph the problem? Okay, and this is why I have this compass here. So we have x squared plus y squared is equal to, 16. No, you cannot use Desmos. We can do it ourselves. We don't need Desmos for this. All right, so our center point is at 0, 0, which is right here. Our radius is, well, square root of 16, which is 4. So 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. So I would definitely locate those points on the grid, but then I would take my compass put it at the tip, at the metal tip at the center, and here we go. Now obviously if you don't have a compass, you can just easily enough sketch it too. All right, for this one, we have a y-intercept, so we have a center at 3, negative 4. 1, 2, 3, 1, 2, 3, 4. Oh boy. And clearly we go off the edge of the circle here. That's our the grid, that's okay. My radius is the square root of 9, which is 3. 1, 2, 3. So I'm gonna put the tip right there. I'm gonna measure down. And here we go. Excellent. And so that's how we go ahead and graph. Now I'm going to make one more video that has one problem on it that deals with how to find the center and the radius when you only have 3 points, and you need 3 points on this one. So I hope this was helpful, and check out the next video.